about the experiments that I did during my postdoc, and I would like to acknowledge my collaborators here, David Kolstedt and Mark Zimmerman in the University of Minnesota and Ben Holtzman in Columbia. So let's get started. Well, melting, as you all probably know, is one of the fundamental manifestations of plate tectonics. And here we see a map of the ocean floor age, where you can see clearly the mid-ocean ridges pop up in red, which means that those are the youngest rocks, where basically melt gets emplaced and forms the ocean floor. So ridges are relatively simple tectonovolcanic chains along which fresh magma gets replaced. And we have these spectacular underwater eruptions as captured on these pictures. So the melt has to migrate from the partially molten mantle toward the Earth's surface due to buoyancy. And as it migrates upwards, it interacts with the surrounding rocks and therefore acts as an important source of information about the mantle below. So how does the melt get extracted from partially molten mantle, and how does it get focused along these narrow spreading centers? We have some constraints from geophysical observations, from seismic and magnetotelluric studies. We can observe that there's a large volume of partially molten mantle. And this resolution of all these studies is basically improving every year. And you can see here, this is a lock resistivity map. So the inference is that where low resistivity is, that we have some melt present. And you can see this large volume that is about 100 kilometers across down to about 70 kilometers depth, which is inferred to be partially molten. And then there's this melt channel that is highlighted right underneath the ridge, where basically all this melt gets kind of siphoned in and emplaced. Now, from chemical composition of magmas sampled at the ocean floor, we can infer what the source of the melt was and which path it took toward the surface. So one very important observation is that pyroxene solubility in mid-ocean ridge basalts increases with decreasing pressure. However, pyroxene is a major constituent of the upper mantle, and it appears that the mid-ocean ridge basalts are not in chemical equilibrium with the surrounding mantle from MOHO pressures upwards. So from about 50 kilometers depth, it seems that the melt does not have enough time or is somehow chemically isolated from the surrounding mantle and does not equilibrate with it. From isotopic composition of the erupted magmas, we can infer the velocity of melt migration from the MOHO up, which seems to be on the order of about 1 to 50 meters per year. And so if we kind of put all these geophysical and geochemical observations together, then we conclude that we have essentially a large volume of a partially molten mantle that has to be somehow tapped so that we can extract the melt, which is the melting percentage in the mantle is relatively low, on the order of a few percent max. So we have to tap a large volume of the partially molten mantle to get enough material out. And the chemical composition tells us that there is some process that allows us for isolating this melt from the surrounding mantle. From the MOHO upwards, and we also know that the melt gets extracted rather fast. So the conclusion from these observations is that there is some process that has to lead to channelization of the melt that allows for this fast extraction, and that is shown here in this figure from a numerical model by Rich Katz and Weatherly in 2012, where they essentially envisage this large kind of partially molten mantle that we've seen in the magnetotelluric image as basically a zone where high velocity of flow occurs within channels that are kind of interpenetrating the mantle around it. So do we see such channels in the field? It's in fact how this argument started. And there are observations from ophiolites around the world that show that the peridotitic bodies, which are basically exhumed pieces of the mantle, are cross-cut by dunite bodies, which are bodies formed only of olivine or predominantly of olivine on a variety of length scale. So here we have a satellite image from Brown and Kellerman, where the scale bar here is 1 kilometer, and you can see all these brighter kind of layers cross-cutting this large peridotite massif in Oman. Here is another close-up where you can see better the topology of these dunite channels, how they kind of cross-cut this peridotitic mantle. And here is an outcrop scale from the Twin Sisters Massif by Krakenberg et al. In 2013. So these these Danite channels seem to be in chemical equilibrium with Morph-like liquids and seem to be of replacive origin, so that they are not dikes, but they formed probably by basically replacive reactions of a percolating reactive melt that has dissolved the pyroxene in them and left behind these Danite channels. So just to make sure that everybody's on the same page, we have here some brief mantle petrology. So most of the mantle is composed of orthopyroxene, clinopyroxene, and olivine. And the fertile mantle that hasn't undergone partially melting is called lherzolite. So that has both pyroxenes, ortho and clinopyroxene. And clinopyroxene is the first material that starts melting typically. So then after some melting, we end up with a Harzburgite, which is what most of the mantle is formed of. So that's a combination of olivine and orthopyroxene. And Danite that I'm talking about is essentially a rock that's formed of more than 90% olivine. So it does not have any pyroxenes left in it. Okay, so what processes can lead to melt channelization in partially molten rocks? So if we start from the basics, the mantle is exhumed underneath the spreading center and it crosses its solidus at some point and starts to partially melt. This melting has to commence at the grain scale between the minerals that take place in this reaction. And the nature of silicate liquids in the mantle is such that melt films get interconnected at very low melt fraction. And hence the initial melt migration must occur through some diffuse porous flow. However, the low melt to rock ratio and diffuse flows are believed to quickly lead to reequilibration, to a chemical reequilibration with the surrounding mantle. And furthermore, the velocity of porous flow is thought to be not sufficient to account for the radiogenic disequilibria that is observed in more basalts. And so at some length scale, we have to move away from this diffuse porous flow that's initially responsible for the melt migration, and we have to enter this domain of channelized flow that is from the moho upwards roughly. And then as we basically get closer and closer to the surface, then the temperature of the surrounding rock also decreases, and we move sort of from the viscous high temperature domain into the brittle low temperature domain, where the rocks, instead of behaving as two-phase fluids, behave as sort of a solid that can be magma fractured by the percolating magma, and then we can get some dikes, essentially. So this is what the I'd say current picture is of what a mantle underneath the mid-ocean ridge does. And so what are the processes that can channelize flow in the upper mantle is the question that we wanted to get deeper into. And there are generally two main causes of melt self-organization that we can envisage. The one is stress-driven melt segregation, which was proposed by Stevenson in theory and was then confirmed experimentally by Ben Holtzman in 2003, which basically is, tells us that if we have a two-phase material, so we have a high viscosity solid and a low viscosity melt in it, and we start shearing this material, then the low viscosity melt tends to accumulate along some zones, and essentially leads to segregation of the melt from the surrounding kind of matrix by deformation. And depending on the ratio of shear stress to buoyancy, which is here expressed in this kind of schematic diagram as this phi g number, we either have highly deformed regions, which are basically where the melt segregation is driven mostly by deformation, or if there's not that much deformation, then buoyancy is the dominant process that leads to melt migration in the mantle. Here on this axis, we have the Deborah number, which basically quantifies the response of the matrix. So if we have a low Deborah number, then everything is viscous. So we are dealing with some viscous two-phase flow, whereas if we're dealing with high Deborah numbers, then we're dealing with brittle matrix that tends to break. And the second process that can lead to melt self-organization is reaction-driven melt segregation, which is here shown on this axis by the Dammköhler number, which basically tries to quantify how reactive the melt is with respect to to the matrix. This has been developed in theory by Einat Aharonov in 1995 during her PhD thesis actually here. And we have done the first experiments that sort of reproducibly tested this theory in 2015. And so you can see that here in the 2009 paper, essentially they don't make any drawings for this, this region over here because there's basically very little experimental data on how these systems behave. So let's have a look on how this reaction basically can lead to some melt channelization. And the idea originally comes from this reaction infiltration instability theory, which was developed to basically explain the increase in permeability during acidification of oil wells. And it hinges on the idea that if there is a positive feedback between flow and reaction, then essentially if we have a reactive fluid that is percolating into a porous material, then the reaction with the porous material, if it locally increases the permeability, which is shown here by this green kind of reaction front, then if this permeability gets locally increased, then further fluid will get channelized in there, and this can lead to a positive feedback process and a runaway essentially channel where most of the flow will be going through this reactive zone. And so in the mantle, what the reaction is thought to be responsible for, or the possible reaction that could lead to this reaction infiltration instability, is that if we have the melt coming from below, so it's undersaturated in the pyroxene component, so it dissolves the pyroxene from the mantle, changes its composition, and precipitates olivine. And the Danite channel is then basically thought to be the result of this reaction where the melt gets extracted and we're left with olivine behind. So the fundamental controls on these are basically, we can think of the flow being controlled by Darcy's law. So we have the flux, which is proportional to the permeability over the fluid viscosity and the driving pressure gradient. And the permeability then depends typically, or is modeled to depend on the grain size and the melt fraction and some geometric constant. So then this is the basis for kind of in the theoretical models, this is based in fluid mechanics. So generally people tend to deal with these non-dimensional numbers that try to capture the behavior of the system. And so the first important number that I'll be talking a lot in this talk about is the Damm-Köhler number, which is basically quantifying the rate of reaction with respect to the transport rate. So here on the top, this quantifies how fast basically the reactions are occurring, and here on the bottom we have how fast the fluid is moving. So that will give us some time scale basically on how quickly will the melt react and equilibrate with the surrounding rock. The second important parameter for these problems is the so-called Peclet number, which quantifies the rate of fluid dispersion with respect to transport rate. And so you can think of this as if you make kind of this channel or this perturbation in the reaction front, then how long does it take for this front to even out and spread out laterally? Both these numbers are not necessarily trivial to estimate for any real systems, but they are very convenient for numerical modeling. And so therefore there has been a lot of work in the modeling community kind of exploring the behavior of these two-phase systems with reaction. And here is a kind of a plateau from Spiegelman's paper in 2001, where they essentially they examined how the Peclet number and the Damm-Köhler number changes the appearance of these kind of high permeability channels through which the flow is coming. So you can see that as the Damm-Köhler number goes up and the Peclet number goes up, then the spacing of the channels gets more and more tight. Whereas if we have low Peclet numbers and low Damm-Köhler numbers, then we have just kind of porous homogeneous flow. Now, despite this being a very kind of popular model to explore theoretically, there hasn't been too much experimental evidence of this reaction infiltration instability in mantle rocks. There's of course a lot of experiments in analog systems, like for example gypsum and water, or or salt and glass beads and so on. But there was the first kind of observation of something that could be a channel was made by Daines and Kolstad in 1994, where you can see here, this is a Harzburgite, so olivine and orthopyroxene that was in contact with alkali basalt. And over the course of the experiment, they observed these kind of the channels that reached into the sample. Unfortunately, these results were not really reproducible. So several follow-up studies that basically tried to get something similar didn't get any channels. And there's one study by Morgan and Liang in 2003 where they could kind of nicely produce something that looked like a channel, but then they show that it's essentially just a crack that got filled by the melt and probably happened during the pressurization here as during the starting basically of the experiment. So we wanted to kind of see why actually the reaction infiltration instability is not really observable in high pressure and high temperature experiments, and whether this is actually a viable channelization process for mantle lithologies. So my kind of question when I went in to my postdoc was what is missing actually. I was originally supposed to study the coupling between reaction-driven and stress-driven melt segregation, but I kind of quickly figured out that actually we don't know much about the reaction-driven melt segregation in the lab, and so I decided to focus on that. And so let's now go through the background a little bit and see what is it that we would need from an experimental setup to study this problem. So as I said, porous flow is governed by Darcy's law. So we have the flux that will depend on the permeability, melt viscosity, and the gradient driving the flow. So permeability will depend on the grain size and melt fraction and some constant. So in the lab, this is something that we can control. We can make rocks with different grain sizes and different melt fractions. So we have control over permeability. And then we need to control somehow the flux, which basically goes into this background melt flow velocity, which appears in both the Damm-Köhler and the Peclet number. So this velocity essentially feeds into the Damm-Köhler number and into the Peclet number. So we need to have some sort of experimental setup where we can vary the fluid flow velocity. And we also then need to have an experimental setup where we can independently of the fluid flow velocity vary the reactivity, which is basically here given by the D, which is the diffusion constant, and the effective reaction rate, which is over here. So we need to have an ability to vary the reactivity and vary the velocity, vary those independently so that we can explore a large range of Damm-Köhler and Peclet numbers and see when the channelization does or doesn't occur. And so to do that, the setup we came up with was essentially is kind of summarized here. So we used the gas deformation apparatus by Patterson, which has many advantages. So the one of them is that it has a relatively large hot zone. And when I say relatively large, then in the high pressure, high temperature world, it's about 3 centimeters long. And we can heat the rock without any temperature gradient, basically up to 1200 or 1250 degrees C. And then we have also the ability to change the pore pressure inside of the experimental chart. So there's a pore pressure system that is essentially feeding here into this porous sink that we used as a sink for the melt, where we can control the pressure from room pressure up to 300 MPa confining pressure. And then with the confining pressure, we go to 300 MPa, so we squish on the whole kind of charge, and then we drive the melt from the melt source through the partially molten rock into the porous sink. And so as we had in this setup, we have a large melt to rock ratio, which we need in order to keep some chemical disequilibrium at these high pressures and high temperatures and these small charges. You need to have a lot of melt, otherwise everything equilibrates rather quickly. And we used as a melt source alkali basalt, which is even more undersaturated in silica with respect to peridotites than the mid-ocean rich basalts. And as the partially molten rock, we have synthesized a number of different rocks. We synthesized a verlite, where we use basically olivine, crinopyroxene, and then we modify the melt fraction by adding some basalt powder. So that allows us to control the permeability. We used Harzburgite, where we use orthopyroxene, and lherzolite, where we basically have all the minerals present and some chromite. And so this is what the kind of setup looks like. At high pressure, we have the melt source, we have a high pressure pushing at the sink and at the partially molten rock, and then we have a low pressure over here, so we will have some melt flow through the partially molten rock. And this is what the partially molten rock starting materials look like. So this is the synthesized verlite that is essentially olivine is here shown in this dark, and white is the verlite with some melt that is present. We have explored 4, 10, and 20% melt for this mineralogy. Here is a Harzburgite, where you can see the OPX is dark and olivine is bright, and we explored here 4 and 20% edit of melt. And this is the lherzolite, where we didn't add any melt. That's for mostly of olivine, some orthopyroxene, and less clinopyroxene with some trace amounts of chromite. So this is our starting material that we synthesized prior to the experiment. And we have essentially a decrease in the melt fraction in the rock. We go from verlite that has the highest melt fractions through Harzburgite to lherzolite, and then also the amount of pyroxene in rock. So initially this is 50-50, and then here we have about 65 olivine and 35 pyroxene. So we also change the amount of material that can react with the melt, basically. The grain sizes are on the order of 5 microns, and so that gives us a permeability in the range of 10 to the minus 16 to 10 to the minus 14 meters squared or so. And so these are some results. So when we this is basically after we have taken out the experiment out of the apparatus, then you can see here, and we cut it in half. So this is basically cut parallel to the flow direction. So you can see here, this is the metal jacket that is surrounding the material and isolates it from the high pressure, high temperature environment. And here the black thing is the alkali basalt, so that's the melt. Here is the partially molten rock, and here in white is the porous alumina sink. And so in the case where we do not apply any pressure gradient, so the pressure in the sink is the same as the pressure outside, then you can see that essentially the shape of this reservoir is unchanged, and there's just minor melt extracted into the reservoir, which is probably originating from this partially molten rock that gets sucked in by surface tension. Whereas if we apply a high pressure gradient, then you can see that the melt source gets kind of deformed and squished, and you can see that the melt sink is filled with melt that migrated through the rock into the reservoir. And if you have good eyes, you can see here also is kind of a remnants of one of the channels that formed over through which it migrated, and I'll show you those in much more detail. So we have done a number of experiments, and this is kind of the summary where we plot the pressure gradient, which is actually the experimental variable that we can control. And then we calculate the melt flow velocity at 2 different temperatures, at 1200 degrees C and 1250. I'll use this color coding throughout the talk, so this will be always the same. So blue experiments are 1200, red are 1250. And then we have here the 3 different rock types. So round are verlites, triangles are Harzburgites, and stars are lherzolite. And then if we have a full symbol, then that means that there are no channels developed in these experiments. And if we have an empty symbol, then that means that we have observed channels. And then there's also an experiment which fractured. So that's this one with the half filled material. And so you can see there is sort of a pattern where essentially the experiments that have low melt flow velocities or low pressure gradients generally do not form channels, and experiments at high flow velocities, high pressure gradients do form channels. And at higher temperatures where the melt flow velocity is higher because the viscosity of the melt is lower, we generally see channels almost always, except for the experiments in lherzolite, which had the lowest permeability and the lowest melt flow velocity. So there seems to be some pattern whether the channels develop or not, which depends on the rate of the melt flow. And now let's have a closer look into how these channels look like and what the main features are in these experiments. So those are some reflected light images of these charges after experiment. So you can see here the scale bar shows 2 millimeters. And then you will see a lot of these kind of black cracks that cross-cut the whole charges always. Those are quench cracks that basically occur during the very end of the experiment where we cool down and depressurize. So they have not been present at the high pressures and temperatures. So these are features that are post-deformation. And so what always develops in all these experiments, irrespective of the exact condition, is basically a reaction layer that develops on the interface between the melt source and the partially molten rock. And if there is no pressure gradient, then this reaction layer is planar. Whereas if we have a pressure gradient, then this reaction layer kind of gets entrained inside and forms these sort of finger-like materials. I would also like to highlight here, you can see there are these larger kind of phenocrysts of olivine that are swimming in the melt. And so here, if we have no pressure gradient, then it tends to settle downwards just by Stokes settling. Whereas if we have the channels coming in, then they get sucked in towards the entrances of these channels. And so you can see here, for example, there's this kind of blob of olivine grains, but there's no clear channel right here, which means that we are just missed the section. So there's basically a channel either before or behind us. And here this is some kind of concentration right by the nice channel and so on. So these kind of olivine grains serve as good melt flow kind of indicators that tells us where the melt was going in these 2D sections. So let's have a closer look on what the reaction layers look like. The reaction layers from Wehrleit, Harzburgite, and Lherzolite at different times basically show similar features. So we have in the source always the glass, and then the reaction layer itself is essentially formed just of glass and olivine, which has a distinct chemical composition from the olivine that is present in the matrix. And then there's always some basically extent of this reaction layer that scales with time and temperature. So this slowly kind of migrates through the rock, dissolves all the clinopyroxene, and leaves behind just olivine and melt. In Harzburgite, we see again the same thing, that we're dissolving orthopyroxene, and we have a reaction layer that's formed of olivine and melt, and the same is true also for the Lherzolite, where we are left with an olivine-rich reaction layer. You can already see a little bit that the melt fraction in the reaction layer is also changing, that there's the least melt in the Lherzolite, which has also the least melt to start with, and the most melt in the reaction layers in the Wehrleit, which has the most melt as it starts. So this confirms that the reaction is occurring in our experiments, that the melt, the alkali basalt, basically is dissolving the pyroxene, is also dissolving some of the olivine, and precipitates new olivine and changes its chemical composition. So this is something that is well known from the petrological experiments, and people have seen these reaction layers for many times. We did some analysis to show how to see how these reaction layers will change the permeability, because just a reminder, the reaction infiltration instability necessitates the increase in permeability due to the reaction. And so the permeability will depend on grain size and melt fraction. And you can see that in the Wehrlites, both the grain size as well as the melt fraction increase as a function of time and reaction progress. And the same is true for the Harzburgites, and the same is true for the Lherzolites. So it seems that this reaction indeed does increase the permeability, and so under some conditions it can lead to this runaway effect, and leads to this formation of the channels. So let's have now a closer look on what these channels look like. And this is because they have essentially an inherently 3D structure, and because we're not really deforming anything, there's no plane of symmetry. And so it really needs a 3D kind of view on these channels. And so what we started doing is to be able to visualize these channels is that we doped the melt with ytterbium, which is a heavy element that is also non-compatible. So it stays with the melt, and it allows us then to have enough contrast in X-ray computed tomography to image the channels themselves. And so I'll show you here a video. Here is just the example of the sample that we scanned. So we dissolved the jacket, and then you can see here the melt source. Here is the partially molten rock, and here is the sink. And so you will have here a pseudo 3D view, and here this will be basically a cut that goes kind of perpendicular to the screen here. And so we'll start in the melt source, and we will go through the partially molten rock towards the sink. So I'll start this. So you can see initially there is basically the melt source, and now you can see these big white blobs that kind of go through the rock, and those are the channels that led to the melt flow. So now if we go back, then you can see here these channels, how they kind of percolate through the matrix until they get into the melt source again. So if we now have a look on what these kind of channels look like right at the or very close at this rock melt source interface, and you can see that in Verlight we have these kind of roundish channels that are distributed sort of homogeneously throughout the rock here. In Harzburgite, we seem to have more channels that are sort of smaller but more closely spaced. And in Lherzolite, we have this very distinct kind of planar feature, which we interpret as a fracture that essentially formed there because this material did not have enough permeability, and we had probably too much of a pressure gradient. So we made a fracture. But clearly you can see there's a distinct kind of topology of these dikes that we can form, and these fingers, which are essentially finger-like features in 3D. So now let's have a closer look in the SEM images, what these channels look like. So here, this is the reaction layer that I've been talking about before, and you can see that essentially the finger is formed sort of as a bulging in of this reaction layer, and this hole is basically just olivine. You can see even some of the olivine phenocrysts that are entrained within the channels, so they have been sucked in from the melt source in here, and then it basically continues, sort of percolates through the material all the way to the sink. This is in Verlights, we have sometimes channels that are even have these kind of melt-free cores that tend to form sort of these like bubbly shapes a little bit. In Harzburgite, we have less melt generally, but again, we see a similar story that we have this kind of bulging in of the reaction layer, where we have only olivine and melt, no pyroxene present, and that sort of kind of wiggles through the rock. And here, this is an example of the Lherzolite fracture, where you can see there's essentially just this little bulge in the reaction layer from which it probably initiated. And there is still some OPX present right next to the fracture, which tells us probably that as the fracture formed, and there was much faster flow, and we kind of stopped the experiment right after that because we've seen that we lost the pressure gradient. So there was not as much time for the melt to react and really dissolve the rock around. Whereas here in these other cases, we never see any pyroxene in these reaction layers. So we can then have a closer look on the chemical composition. So those are electron microprobe maps. So here, this is the silica content, which is nicely basically highlighting the presence of olivine. So olivine has the lowest silica content, so it's shown in blue. Then generally the melt is intermediate, so that is greenish to yellowish, depending on how much pyroxene it has dissolved. And then in this case, this is from Harzburgite, so the orthopyroxene has the highest silica content, so it's red. And you can see, again, this reaction layer, which is formed only of blue olivine. And the same is true for this whole channel that basically has formed within the experiment, how the melt kind of got intruded here and dissolved all the pyroxene in this area. You can see nickel also gets kind of enriched in this area. And then a good marker for melt itself is sodium. So sodium is basically present only in the melt. As I told you before, we put some melt into the starting material. So you can see that there are some little kind of blobs of melt to start with, which is what we use to modify the permeability. But then clearly the melt fraction is increased within the channel itself. And then the ytterbium, which we use for doping the melt only in the source, basically shows us where the melt from the source is migrating. So you can see nicely that essentially the melt clearly from the source made it all the way in here into the rock because it shows ytterbium, but it did not make it, for example, over here where you can see some sodium. So there is melt, but there has been no communication between this melt and the melt from the melt source. So it's clear that the channelization leads to an increase in the volume percent of olivine in the reaction product. So we have much more olivine in experiments where we have channelization than in experiments where no channelization occurred. And we can also see the chemical changes that occur during the channelization here. This is an example from the Verlight experiment, where again in green is the melt source, blue is olivine, red is this time clinopyroxene. And you can see the melt kind of changes from this greenish color towards this yellowish to orange. So it gets more and more saturated in silica as it dissolves the pyroxene. And it gets saturated also in calcium, because here we're dissolving clinopyroxene. And it gets depleted in MgO and FeO because it's precipitating some new olivine in there. The general channel morphology is kind of illustrated here by these three experiments. So if we have no channelization, then we basically have a nice sample where there's not much deformation to the melt source, and there's no melt migration through the rock, so we have just a reaction layer. And this is a sample that was annealed under a low pressure gradient for a short amount of time. So there's this kind of two channels that basically made it all the way through and have extracted some of the melt from the source. And this is a long experiment where we can see these kind of massive channels that cross-cut the whole partially molten rock and extract the melt from the sample. So we tried to quantify the topology of these channels a little bit more by basically analyzing their position, and this is just a figure where we basically scale the area of the channel by the symbol size, and you can see essentially that within Verlight over 300 minutes experiment, we have these kind of channels that make it from the source, which is here shown by yellow, all the way to the sink, which is shown by blue. Then we have basically three main channels that penetrate all the way through, and then we have a number of smaller channels that got starved and didn't make it. And here, this is what the topology of the channels looks like in Harzburgite after a shorter experiment, where you can see there's much closer spaced, smaller channels. But again, we have just 2 or 3 channels that make it all the way through. But that's all that you really need to extract all the melt. Given that there are so many variables, temperature, time, then the composition and so on, it was hard for us to get some kind of coherent series where we could kind of explore more how this topology changes of the channels. But it seems that they sort of tend to coarsen over time. We have tried to quantify essentially the volume that those channels occupy, and they occupy on average only about 2 volume percent of the sample. So they are not replacing the whole sample. They are relatively small, or relatively occupy only small volumes, but of course all the melt is going through them, so they are very important for the melt migration. And so you can see here, this is from one experiment where we quantify the 3D length of these channels versus the volume that the individual channels occupy. And so you have a lot of short, non-voluminous channels, and then you have just a couple basically that make it all the way through, but they are the thickest channels. Interestingly, the spacing of the channels is pretty much constant within what we can resolve. So that's about 2 millimeters, and there's not much of systematics with in between the individual runs. So if we sort of wrap up the lessons that we learned from these experiments, then we have devised an experimental system that allows us to basically control these 2-dimensionless parameters, the Dunkerler and the Peclet number, by modifying the melt flow velocity and modifying the reactivity by choosing different grain sizes, different minerals, and different temperatures. And so then if we basically take all the experiments together and calculate what our best guess is on what these values are, then we can see that we basically cover a huge range of Peclet numbers as well as Damköhler numbers. And generally all the experiments fall into this trend, which is heavily governed by basically this relationship of the velocity in the Peclet number and here in the Damköhler number. So this is just 1 over velocity and velocity, which gives these large trends. And then you can move kind of parallel to these trends by modifying the reactivity of the materials. So generally, if you start anywhere, then as your permeability, as your reaction progresses, then your permeability can increase, so your Damköhler number can increase. And as your reaction kind of effective reaction rate decreases, then you can sort of go towards smaller Damköhler numbers. What you can see is that essentially all the experiments tend to have a constant product of the Damköhler and Peclet number, just because of the way how these kind of quantities are defined. And that is an interesting observation that basically is comparable to the results from the modeling community in Spiegelman, where you can see that the spacing of the channels, if you move along the diagonal here, is basically staying constant, which is what we see. And so you can't really, in a physical system, kind of independently change the Peclet number much from the Damköhler number, because they are sort of coupled and there are interconnections, for example, between the reactive rate and the velocity and the permeability, that if you make your grain size smaller, then your reaction rate should increase, but your permeability also must decrease, because all these things are somehow interconnected in the physical system. So we don't have really that much freedom to fully explore this space. And generally the Damköhler and Peclet numbers seem to be a rather poor predictor for the presence of channels in our experiments, that we have some that basically form channels right next to some that don't form channels. The additional, of course, constraint here is time that is not really taken into account in all these steady state models that clearly. So to conclude, we have shown that reactive melt migration can lead to melt channelization at high pressure gradients at fast flow velocities in these mantle lithologies. The channelization is clearly facilitated by a high melt fraction and high pyroxene content in the rocks and a viscous matrix. The melt-rich channels consist of olivine and melt with no clinopyroxene or orthopyroxene. So it seems that this reaction, if we would extract the residual melt from it, then we would be left behind with a dunite channel. The melt channels have a finger-like morphology, which is in contrast to the tabular dunite bodies, which are always tabular. And that probably tells us that there is a significant influence of shearing in nature, because the stress-driven sheets of melt tend to be actually planar. So there must be some combination of these two processes working together in nature to extract the melt. And fracturing basically occurs if we have low porosity and low pyroxene content, when the brittle matrix basically is just not so viscous enough to allow for this viscous fingering to occur. And the fractures are clearly different from these channels. They have a very planar morphology. And channelization indeed increases the bulk permeability as well as fracturing. So both of these processes will massively increase the permeability of the rocks and allow for a much faster melt extraction than if they wouldn't occur. So with that, thank you for your attention, and I'm looking forward to your questions.
Yeah, thank you so much, Matej, for the wonderful talk. Anyone has questions, you could raise your hand or type your question into the chat. Okay, so Yuri.
Yes, interesting results. Thank you for your talk. I'm wondering if you can estimate the fraction of melt transported by dikes versus reactive transport, just in nature. I mean, not just in experiments.
Oof, that is a very difficult question. I don't know the answer. There might be some geochemical signatures, but the geochemical part of this whole story is to me the most mysterious one, frankly. So I would think that generally the dikes won't be probably too important at higher depths, because just generally the mantle is pretty hot. So I would expect that the brittle processes will be most important in the crust rather than in the mantle. But it's more
on the time scale of melt propagation, right? So we're talking about viscoelastic material with fairly high viscosity. So if things are happening fast, it would behave more or less elastically, right, on short time scales. So if I just rephrase my question a little bit, if you have melt fractions on the order of several percent, what would prevent dikes from forming and just draining that melt at much higher rates than the reactive transport would?
And what prevents the melts from forming if you have large melt fractions? Well, I think that's like the Alan Rubin did to figure out all the heights that you need to have for basically a hydro or magma fracture to self-propagate. And I think the numbers for that is that you would need to have a column of melt that's rather large, if I remember right from his solutions. So I think it seems to me to be the problem that you need to accumulate somewhere a decent amount of melt in the first place. Does that?
Okay. Yeah, we can discuss the details offline. But another question I have is of technical nature. I'm wondering, in your experiments, do you have any problem with melt escaping at the contact with the wall?
Yep, absolutely. That it was one of the things that kind of plagued the experiments initially, and that is essentially there is a non-zero permeability between the wall of the sorry, I'm looking for the proper image. So there's a non-zero permeability between the jacket and the partially molten rock itself, and so that sort of limits the experimental space we can explore, because you need to have enough melt in the partially molten rock that the melt goes through the rock and not through through this interface. And what we also started doing then is that I just put basically a thin nickel layer right at this interface that was kind of punched through. So you can see this bright here. That's a nickel layer that is basically helping to kind of seal this space from the melt, so that you force it more to go through there. But yeah, the experiments generally were quite challenging. It's difficult to keep the pressure gradients without any leaks at these high temperatures and pressures for long enough for the channelization to occur. It's
yeah, thank you.
You're welcome.
So Dan.
Hi, thanks for the talk. That was really, really awesome. I'm on a larger scale, like in the mantle beneath the mid-ocean ridge, how large do you think, and how long-lived do you think these channels could be, given that the mantle is sort of, slowly convecting and deforming, but also that these processes are probably happening on a timescale faster than that, and there's probably plenty of melt around because you have a continuous source of melt being generated. Do you think these channels are long-lived, and how big could they get ultimately?
I think from the observations in the field, basically they can be kilometers thick, right? And so one of the kind of problems, if I remember right, was that if you want to do a kilometer thick channel by just basically reaction, replacement, then that would take you just a very, very long time, because generally the growth of these reaction layers scales with the square root of time, because it's a diffusive process, and so the thicker they get, the longer it takes. But clearly, once you have actually kind of active melt flow and advection of the kind of fresh melt towards the unreacted rock, then that kicks up the reaction rates quite a bit. So we can see that the channels which are quite voluminous in the end form over a couple hours in the experiments. So clearly, once you start flowing the melt, then you are no longer limited by this diffusive length scale, because you have an additional help from the active flow of the melt. And so that, to your answer, how thick they can get, I would say, I don't know, if we trust like elements observations from the Oman ophiolites, and they can be kilometers thick. And then how long they last, that will sort of depend on how long it takes for corner flow to kind of turn them around and get them out of that zone. So, my guess would be millions of years probably, but it's just a wild guess. I bet somebody has looked into detail in those timescales.
Cool, thanks, appreciate it.
You're welcome.
Tianze.
Thank you, Matej. Very nice talk. Maybe I have missed it, but what stress state did you subject your samples to, and how are those states compared to the real stress state near mid-ocean ridge?
So the stress state here is somewhat, they are basically, we don't put any differential stresses on the rocks. It's just hydrostatic, pressures that are pushing on the whole sample assembly. So we have, and we did all these experiments at 300 MPa confining pressure. So that's about 9 kilometers depth or 10 kilometers depth or something like that. So that scales roughly. Then what we did vary is the pressure gradient or the pressure difference, which of course is orders of magnitude higher than you would expect in nature based on buoyancy, because we basically can, have a 300 MPa pressure gradient over a couple millimeters of a rock, right? So the pressure gradients that we are applying in the lab are much higher than you would expect in nature. What is sort of interesting when you look on the calculated melt velocities, you get into the ballpark of nature, and that's mostly because the permeabilities of these so the melt flow velocity here in microns per second is like 10 microns per second. So that gives you to something. The faster ones are about meters per year, I think. And so the grain sizes and the permeabilities of the rocks are much lower than what we would expect in nature. And so that sort of counteracts itself a bit. But of course, the pressure gradient you can see here in MPa per millimeter, we have just a very high pressure gradients. That's sort of the necessity to make the melt flow at a appreciable velocity in the lab.
So do you mean that in reality, beneath true mid-ocean ridges, the flow will be faster, or it will be slower, or?
The flow will be on the same order of magnitude if we, trust all these calculations and good enough constraints. I mean, there's a lot of uncertainty in this. Like we do not measure directly the melt velocity. We assume that we have the pressure gradient. We assume that we can calculate the permeability of these rocks based on the grain size and the melt fraction, right? So if we have, there will be some errors in all this. So I would say, the relative position of all these points is solid, I think, but how exactly this y-axis is, what the real velocities are is, I think, sort of much harder to constrain.
Okay, thank you.
You're welcome.
So there's a question from the chat window. Joyce, do you want to unmute yourself and ask a question? Can you read, Matej?
Yeah, I see
Sure.
that.
Can you hear me? Yeah, I posted in the chat the question. Thank you for the nice talk, Matej. So I was wondering, is the Darcian-like flow a good approximation for melt channelization in this case?
That's a very good question. It is not once the melt is channelized, and especially once you have these like really melt rich, portions. It will, when you basically are dealing more with suspensions than some porous media. But generally, all these kind of calculations that we do, and also in the numerical models, they are valid as the initial state from which the system evolves. So you sort of, calculate what your melt flow velocity is at, let's say, T0, when you just start the experiment. But of course, once you start, channelizing the fluid and changing the local permeability, then you will have we will have basically spatially dependent flow velocities. And once you get the high melt fraction, then you're more dealing with some suspension problems rather than porous flow in a porous media. But the initial assumption for the relatively low melt fractions is probably justifiable, or at least that's the best we could think of what to do, and is generally accepted as a reasonable approximation.
Thank you. I'm also wondering, so in that case, at some point when you hit the limit of the Darcian light flow, then maybe there's a better way to look at the Dem-Kohler number versus the what's the other number?
Number.
Yeah, Peckley number. Yeah, exactly.
Yeah,
so then that might change things a little bit of characterizing the flow itself, and that might be really interesting.
Absolutely. Yeah, I think frankly, just all the variables that one has to feed into the Dem-Kohler and Peckley number equations are just very poorly constrained. It is not easy to, if I can make it all the way in there, it's like, what is the reactive area available for reaction in these rocks is generally difficult to estimate. So you just do your best with the grain size and use some approximations of the shapes and so on. But it's I would say it's somewhat unsatisfactory, or that was my conclusion from these, that we can try to put some numbers on all these individual variables, but we have a relatively poor constraints on them.
Thank you.
You're welcome.
Hi, Matej. Maybe I have a question. I was thinking, what do you think, like melt migration can generate earthquakes?
Yes. Well, yes. Certainly there are actually even some nice experiments from Luigi Burlini in ETH when he was there, when they were listening to the. It's not necessarily like an earthquake. They were more listening to like tremor-like signals. That you could hear basically the melt motion in experiments, but it wasn't necessarily like an earthquake-like signal. It was more a tremor-like signal. And I guess generally, with any sort of, you can do magma fracturing, or so you can kind of do a hydrofracturing earthquake or things like that with the magma. So I think certainly the melt will change the pore pressure conditions and potentially induce failure that could be seismic.
Okay, thank you. So if there's no more questions, thank Matej again for the wonderful talk.
Thank you very much. And if you have any further questions, just shoot me an email. I'm happy to talk more about these experiments.
Okay, yeah, thank you so much.
Thank you.
Yeah, just a few announcements for next week. So next week we will have 2 talks, one on Monday from Professor John Corsi, and another one on Tuesday at the same time. And we will send out announcement later this week. Okay, so thank you everyone for coming to this seminar, and we'll see you next week.
Thank you all.
Yeah. Yeah. Thank you, Matej.
Thank you. Enjoy the surfing.
Yeah.
I haven't talked about this in such a long time. I just
it went pretty well.
Thank you.
How was your experiment like? Is it normal at MIT?
Yeah, we're doing everything back to like more or less normal. We just have to have masks when we're with people, and you have to get tested twice a week, and everybody has to be vaccinated who's on campus. So
okay.
Our current status here, and yeah, it's better. It used to be quite miserable when we just had everything closed down, and I was nobody was working in the lab, and everybody had to be paid. So it's like, no, it's so sad.
Yeah. So okay, it's roughly the same, but we don't need to be like tested every 2 weeks.
We have actually, the students have to be tested twice a week, and then we as staff are just once a week.
Oh wow, that's pretty intense.
I'm a little bit afraid of the winter. I hope that there won't be another surge, because I really I have a lot of teaching this semester, and just the idea of Zoom teaching again kind of gives me the creeps, frankly. You know.
Okay, but now you are teaching in person?
Yep.
Or-
Yeah.
Okay, okay.
Yeah. It's much nicer than to teach to, you know, black kind of turned off camera.
What classes are you teaching? Structural geology?
Yeah, I teach structure and flow, deformation and fracture of Earth and planetary materials or something like this. That's we have merged with Brent Minshew. I don't know if you met him. You did probably.
Yeah.
We merged like continuum mechanics and physical properties of rocks and rock deformation classes and some like tectonics into one class, so that we get more students. And we just realized we always start, you know, teaching tensors and stress and strain, and before you get to anything interesting, you are halfway through, right?
Yeah, every class starts with that, like stress tensor.
We try to optimize this a little bit to get more, you know, more teaching and less repetition. But
Oh,
that's going
cool.
so far,
Yeah.
yeah.
Wow. So how many students do you have right now?
We have 9 in the one class and 4 in the other. So, you know, 9 is a fairly big class for us, and 4 is kind of okay-ish on the smaller side. But it's,
I realize how many students in your group.
oh, in my group now, I have 3 primary and I have then 3 postdocs or 2 postdocs, and Uli is a lab tech basically. So we're 6. And
Wow.
second general students too. But now less than before. Before I had for the pandemic I had like 4 or so. So
Wow.
every week 8 hours of Zooming just with everybody in the group to make sure, you know, that they kind of are okay. I got pretty tired.
It's nice, like people like doing experiments. I feel, especially at MIT.
So it's really nice to be in the lab again and like do something with hands. You know, it's
Yeah,
entertaining.
great.
Will you go to AGU?
I'll be online.
Online. Oh.
Yeah. Still keeping online.
Yeah.
How was your little daughter?
She's good. She's more and more opinionated, you know. So now she like always like said like no, and she doesn't want something. But
Okay.
they play quite nice, so they are good brothers and sisters. So we're but
Interesting.
yeah, they are fun. Crazy.
Yeah, especially at that small age, I think it's really cute.
Yeah, that's true. Yeah, very cute.
Yeah. Nice.
Yeah, so we have still the whole day in front of you, right? I'll soon, it's nasty here, raining. I'll soon have to go back to pick them up actually from daycare and cook the dinner.
Okay.
And work again in the evening.
Oh, yeah. Oh, yeah. It's like 4.
Yeah.
Okay.
This was a good timing though. Yeah. And all day.
Okay. Yeah.
Well, so thank you very much for having me again. And yeah, I hope to see you in real 3D at some conference sooner, you know.
Yeah.
Yeah.
We hope we could.
Start surfing, you know, everybody has to surf at Scripps from what I know.
Yeah, I mastered that skill. Okay. Yeah.
Have a great one.
Yeah, you too. Okay.
See you later. Bye-bye.
Bye-bye. 40.